Hi there, my name's Steve Tucker from the University of Aberdeen, and together with my colleague Mintu Nath, we're going to provide a demonstration of iDrug, that's Interactive Dose Response User Guide. Now, we did demonstrate an early version of this last year, but generously funded by a further BPS education grant, we've added substantial amounts of new functionality to the application. Just to remind you in terms of the perspective of our application and its design, we all know of course that pharmacology is a very practical discipline and involves generating quite a lot of data. And therefore our programs need to equip students with experience and understanding of how to appropriately analyse that data. Now, we've chosen to focus on concentration response relationships because of course they're fundamentally important to learning and teaching pharmacology. And of course, while students maybe understand how dose response curves operate and the sorts of things that happen to dose response curves under certain circumstances, do they actually understand the underpinning statistical models that are applied in plotting dose response curves? And that's what we aim to kind of bring with our iDrug application. The data and its presentation and the way that we analyse it, but build into that an understanding of the underpinning statistics. Now, of course, it also helps us overcome certain barriers to practical teaching. Of course, we're all faced with increased class sizes and timetabling constraints. There's an emphasis on online or flexible delivery, and of course cost is always a barrier there. And what iDrug attempts to do is provide a kind of simulated alternative that can perhaps take the strain out of some of these constraints. Now, it has to be said that this project has now been supported by 2 BPS teaching or education grants, and we're very grateful to the BPS for funding us to do this. And what we've tried to do is design this flexible, interactive app that offers not only simulation, but access to the underpinning and very important statistical modelling analyses that are applied within concentration response curves. In terms of the kind of updates that have been added this year, my colleague Mintu will take over and talk you through those specifically. But what we've tried to do is include different types of concentration response experiments, so contractile and relaxatory, and we've now added antagonist models in there as well, so that this kind of opens up further analysis such as shield analysis and dissociation constant calculations, etc. And it's all embedded within this very flexible and easy to use, easy to access application, as Mintu will demonstrate now.
Here we'll demonstrate iDrug. Select the type of dose response from the drop-down list. Select the available dose response experiment and the different concentrations. And then you click the button Run Experiment. The trace on the right illustrates the data generated in a contractile dose response experiment presenting the response as smooth muscle tension measured in grams to different concentration of drugs. Generally, mean or median values are recorded and the response data are transformed into percentage change for subsequent analysis. But this is just one snapshot of the experiment. In real time, we will do multiple replicates that you can do in Simulate Data option. Here, you move the slider to select the number of replicates for each concentrations. And then you click Simulate Data. The data will be presented on the right-hand panel, both graphically and in tables. You can also download the data by clicking the Download Data option. The simulation features is an optional one. Setting a seed value will allow you to generate an identical dataset in each new session for a given combination of input values. iDrug implements the log logistic model, the most commonly used model to feed the dose response data. The generalized log logistic model is characterized by 5 parameters: B, which is the steepness of the dose response curve; C is the lower asymptote or the lower limit of the response; D is the upper asymptote or upper limit of the response; E denotes the effective concentration 50 or EC50, and F is the asymmetry factor of the curve. Using constant values of some of these parameters, iDrug implements 3 flavors of models, models 1, 2, and 3, which are 3, 4, and 5 parameters model respectively. All these model parameters have therefore underpinning biological context, and hence the data could be explored to get an idea of those model parameters. Explore Model tab allows you to select the values of model parameters on the slider and review the fitted lines on the right, conditional on the selected parameters. Assess how specific parameter values controls the shape of the fitted line. Select Model tab will give you options to fit 3 different types of model. Select all 3 models and click the Fit Model. This table provides the estimates of the model parameters for those different models, as well as some important summary statistics like negative log likelihood, AIC and BIC. You can also see those AIC, BIC and negative log likelihood graphically. Generally, smaller values of AIC and BIC are considered for parsimonious models that best fit your data. For example, in this scenario, we can see Model 2 having the smallest AIC and BIC among these 3 models. The True Model tab will give you the actual parameter values that iDrug used for simulating the data. The Final Model tab will allow you to fit the model that you have just identified. For example, we have identified the Model 2 is the best. Here you select the Model 2 and then you select the predict response for given concentration as well as the predict effective concentration for producing set of percentage response. And then you click the predict button. Summary of fitted model will be provided, as well as it will give you the predict response, predict effective concentration and the dose response plot. iDrug will also produce a set of residual plots. The model has underlying assumption that residuals are normally distributed with zero mean and constant variance. The assumptions on normal distributions can be checked through the histograms as well as the QQ plot. The plot of residuals against the fitted value will provide you an idea about the constant variance assumption. Observations with higher Cook distance are more influential. Similar to contractile dose response, you can also do the relaxatory dose response. The response will go down with the increased doses. Next, we simulate the data for the relaxatory dose response, and as you can see, the response is going down with increasing concentrations. The same way, we can also explore the model to see the parameter values or the estimates which best fit my data. Finally, in the Select Model tab, you follow the same strategy to find the model that best describes your data. From this Model Comparisons tab, again we see that possibly the Model 2 best model for this purpose. In the Final tab, you select the final model and do the prediction exactly the way as we have done before, and it will provide all the results as we have seen before. For the contractile dose response, we can also do more complex dose response experiment. Here, we are using agonist as well as agonist and antagonist to simulate the data. There are 2 dose response plot here, one for the agonist and one for the agonist and antagonist. Explore model, you can do exactly the same way, change these model parameters in the slider and see the estimates of the model parameters that best describe your data. Modeling options are more complicated for these scenarios. Here, in theory, you can have equal or unequal parameter values for agonist and agonist plus antagonist. For example, here we have considered C, D, and F as equal for these 2 scenarios, while B and E, they are unequal. You can explore the summary of different models and decide the model that best fits your data. For example, again through the model comparisons, AIC, BIC, and negative log likelihood, we see the Model 2 is the best. So in the Final Model tab, we can select Model 2 and the other model parameter values and the other input values and click Predict, and then we'll get summary of those models, predict response, predict EC, the dose response plot, and the residual plots, and we need to explain exactly the same way. So here we demonstrated how we can use iDrug to conduct several types of dose response experiment where you can generate the data, feed the model, and use the model for further explanations.